Where's the coldest place on Earth? Origin, Antarctica, discovered via a NASA satellite, is a bone-chilling minus 92 degrees Celsius. If you spilled part of your coffee on the ground, it would probably land as ice. But that is still much warmer than what we are talking about today. In this video, I wish to present the third law of thermodynamics. This law is fundamentally related to the entropy of a system and establishes the concept of absolute zero. The third law can be expressed by stating that the entropy of a perfectly crystalline solid is zero at absolute zero. Note that by definition, impurities in a crystal would prevent it from being ideal and from reaching absolute zero. Absolute zero is part of the Kelvin temperature scale. It corresponds to minus 273.14 degrees Celsius or minus 459.67 degrees Fahrenheit. To remind ourselves, the Kelvin scale sets zero as an absolute quantity. Degrees are not normally used when giving a value in Kelvin, so instead of saying 0 degrees Kelvin, we just say 0 Kelvin. Now back to our perfect crystal. When we reach absolute zero, all the energy associated with atomic motion has left the crystal. The atoms become perfectly still. The problem with reaching absolute zero is provided by the second law. Since heat always flows from higher temperature to lower temperatures, it is clear that heat will always want to instantly move into any system approaching absolute zero. To understand entropy and understand absolute zero, it is best to introduce the concept of microstates. A microstate can be represented as all the possible ways in which atoms can be placed into different energy levels. Imagine 3 atoms occupying a system which is divided into 3 connecting rooms. Each room is a different energy level. You can place all 3 atoms in the lowest energy level or in one of the other 2 for a total of 3 possible microstates. Alternatively, you can place 2 atoms in one of the energy levels and a single atom in one of the other 2, resulting in 6 more microstates. Finally, you could place a single atom in each energy level. In total, you would have 10 possible microstates. When absolute zero is reached, all of the atoms must be in the lowest microstate, resulting in a net entropy of 0. There is a simple expression which can be used to calculate the entropy of a system. It states that entropy, S, is equal to Boltzmann's constant times the natural log of the number of equiprobable microstates. At absolute zero, we just learned that all the atoms must occupy the lowest microstate. Since the natural log of a single microstate is 0, then the entropy of the system is equal to 0. Another way to express the third law of thermodynamics is to state that absolute zero cannot be reached by stepping through a series of microstates. More precisely, absolute zero cannot be reached through a finite sequence of cyclic processes. To understand more about absolute zero, we will introduce the concept of negative temperature. You might say, wow, how can a temperature be more negative than absolute zero? This must be nonsense. Negative temperatures can actually exist when we consider a system which can be characterized by electronic or nuclear spin. That is related to my own field of magnetic resonance imaging. So let's learn a little about MRI. In medical MRI, we typically detect signals from hydrogen atoms in water molecules. The hydrogen atom has a nucleus, which is made up of a single proton, as you may remember from high school. Protons have a positive charge. Interestingly, the proton has a property known as nuclear spin. Because it is charged, the proton therefore also has a small magnetic moment. Normally, all the little magnetic moments from the hydrogen atoms in your body are randomly oriented. If an external magnetic field, however, is applied, they begin to precess like a top around the main field. When they do so, they can rotate either parallel to the main field or spin up, or alternatively, they can be anti-parallel or spin down. These two populations differ slightly in energy. If the atoms are able to remain in thermal contact with their surrounding lattice when this happens, then at room temperature, a very slightly greater amount of nuclei will become aligned parallel to the magnetic field and will be spin up. We will have just two energy levels, with the spin up protons in the lower energy level. The amount of protons in the upper or the lower energy state is given by what is known as the Boltzmann equation. It depends solely on temperature and the energy separation between the energy levels, known as delta E. The energy separation between spin up and spin down energy depends only on the type of nuclei we are studying and on the strength of the external magnetic field. Delta E becomes greater with stronger magnetic fields, and that is why MRI scientists always want stronger magnets. You end up with a bigger difference between the amount of spin up and spin down hydrogen atoms, and that gives you more signal and better pictures. Now let's return to the Boltzmann equation. As temperature moves to infinity, the population of the nuclear spins in each state becomes equal, as e to the 0 is equal to 1. This is telling us something about the definition of temperature as well. Infinite temperatures imply that all states are equally populated. That would not be very useful for MRI, since no signal could be extracted from such a system. If we could reach absolute zero, the lower state would become exclusively populated. To reach negative temperatures in MRI, all we need to do is put more spins in the upper energy state than in the lower state. In that case, the temperature in Boltzmann's equation becomes negative. In practice, this is accomplished with electromagnetic energy in a process which is called polarizing the sample. We could try to reach absolute zero by approaching it from negative values, but the same restrictions would apply. Absolute zero cannot be reached from either direction. To see why, let's examine the spin distribution above and below absolute zero. When we approach from infinite positive temperatures, all the spins end up in the lower energy state. But when we approach absolute zero from negative infinite temperatures, they all end up in the higher energy state. There is a clear discontinuity at absolute zero, and this represents another visualization of why absolute zero can never be reached. We studied negative temperatures to gain more insight into the third law. But remember that such temperatures represent specialized states which do not exist at random in nature. Well, that does it for the third law. If you enjoyed this